Alright, so what we're going to do in this video is we're going to learn how to solve a differential equation that you already know how to solve. Alright, so y double prime minus y equals negative t. We already learned how to solve that. In fact, we've learned two ways to solve that in chapter 4. But now we're going to learn a different way to handle it. So you may remember from chapter 4 that we could solve this first by finding a particular solution, and then also by finding a homogeneous solution. And then we know that our general solution is just the sum of those. Once we find our general solution, we apply our initial conditions to find the appropriate coefficients that satisfy those initial conditions. In chapter 4, we learned two different ways of finding that particular solution. We learned that we could do it with the method of undetermined coefficients or variation of parameters. We also learned that those two approaches each have their advantages and disadvantages. The method of undetermined coefficients works great whenever the right-hand function is something that fits into one of our nice categories, like a polynomial or exponential function or sines or cosines. But it doesn't work so well if that right-hand side is some other type of function. Variation of parameters works great because it can handle a wider variety of functions on the right-hand side. But then its drawback is you have maybe a couple of ugly integrals to do. So they both have their advantages and disadvantages. We're going to learn a new approach here using what we've been talking about with Laplace transforms. And just like everything else, it has its pros and cons. With Laplace transforms, the advantage is that it can take some differential equations and turn them into some really easy equations to solve. The disadvantage is, or I guess one of the disadvantages that you could run into, is that it really only works if you're dealing with an initial value problem. In other words, if I don't hand you these initial conditions, then we can't use this method. The reason is, if you look at the properties of the Laplace transform that I have written up on the top right corner, you saw these properties in a previous lesson. In particular lesson, or properties 2 and 3 here, we've learned that the Laplace transform of the derivative of a function is equal to s times the Laplace transform of the function minus f of 0. Now notice this f of 0 is exactly what's given to me in this first initial condition. So in other words, with this initial value problem, I know exactly what number should go in place of f of 0. F of 0 is 0 in this particular case. Similarly, in the third property listed here, the Laplace transform of f double prime equals s squared times the Laplace transform of f minus s times f of 0, which again, we know exactly what goes there with this initial value problem. In this particular case, y of 0 equals 0, so we would put a 0 there. And then f prime of 0, that's what was given to us in our other initial condition. So in this particular case, f prime of 0 would equal 1. So we would put a 1 in place of f prime of 0. So if I'm given initial conditions and I apply these properties, I'll know exactly what numbers to put in place of f of 0 and f prime of 0. However, if I'm not given initial conditions, I'm given just a plain old differential equation instead of an initial value problem, then there's not much I can do here with this method because I'll have no idea what numbers to plug in to these spots. Alright, so it kind of fits the theme of everything we've been talking about in chapter 4 and now in chapter 7. all of these methods have their advantages and disadvantages. So there's maybe some others we could talk about with Laplace transforms, some other advantages, some other disadvantages, but let's get into solving this problem. All right, now the basic process for solving these initial value problems is we'll start by taking the Laplace transform of both sides of the equation. So the Laplace transform of y double prime minus y equals the Laplace transform of negative t. Okay, now the fact that the Laplace transform is a linear operator tells me that I can break this up on the left-hand side to say just the Laplace transform of y double prime minus the Laplace transform of y. And on the right-hand side, let's go ahead and pull that negative sign outside because, again, since it's a linear operator, constants can be pulled out. So this is negative Laplace transform of t. Now, the notation I'm going to use here, I'm going to say that the Laplace transform of y of t, remember when we take the Laplace transform of a function of t, it gives us a new function in this new domain, and we usually assign it the variable s. So we're going to call this some function of s. We don't know what this function is, at least not at this point, but I'm just going to call this Laplace transform of y of t this capital Y of s. Okay, notice we have that showing up right here. So that piece, I'll just call that capital Y of s. But first, let's take care of this Laplace transform of y double prime. Now again, let's use this third property. I'm doing the Laplace transform of a second derivative. So according to this property, this is going to be s squared times the Laplace transform of y minus s times y of 0 minus y prime of 0. Okay, that's the Laplace transform of y double prime. And I'll go ahead and rewrite everything else just like it was. I had the Laplace transform of y equals negative Laplace transform of t. All right, so now let me clean things up a little bit. Just like I was saying over here just a second ago, I'm going to rename this Laplace transform of y. I'm going to call it capital Y of s. So I have s squared times capital Y of s minus s times, now here's where we use our initial conditions, right? What is y of 0? Y of 0 is 0, so s times 0 minus y prime of 0. Look back up to our initial conditions. Y prime of 0 is 1. So minus 1 minus the Laplace transform of y. Again, we're naming the Laplace transform of y. We're just going to call it some function capital Y of s. On the right-hand side, what's the Laplace transform of t? If you look back in your table of Laplace transforms on page 356, or if you have it in your notes, the Laplace transform of t to the n equals n factorial over s to the n plus 1. In this case, we have t to the first power. So I have negative 1 factorial, which is 1, over s to the n plus 1. So that would be s to the 1 plus 1, so that's s squared. All right, so what we have here, after taking the Laplace transform of this differential equation, we really just have an algebra problem. It's no longer even a differential equation. This is just an algebra problem that we want to solve. Let's solve to find out what this function y of s is. All right, so first let me clean this up a little bit. I don't need that s times 0. Let's see, so s squared times y minus 1 minus y equals negative 1 over s squared. And it's understood here that these capital Y's are functions of s. I'm just not writing it just to make it look cleaner, I guess. Let's solve this equation for y. Now again, this is just some basic algebra. I'll start by moving that minus 1 over to the other side. So I have s squared times capital Y minus capital Y equals negative 1 over s squared plus 1. Now if you'd like, we could go ahead and get a common denominator on the right hand side and combine that into a single fraction. I can rewrite this 1 as an s squared over an s squared. So then when I add these, I have negative 1 plus s squared over s squared, or s squared minus 1 over s squared. And this is equal to s squared times y minus y. On the left-hand side, I'm going to go ahead and factor the y out. Factoring the y out, I'm left with s squared minus 1 on the inside. And now we finish solving for y by dividing both sides by s squared minus 1. So y equals, notice if I divide both sides by s squared minus 1, we already have an s squared minus 1 showing up in the numerator. Those are going to cancel, and we're left with just 1 over s squared. So now this function, y of s, that we were talking about earlier, we know what this function is now. Y of s is 1 over s squared. So after taking the Laplace transform, this turned into a basic algebra exercise to find this function capital Y of s. Capital Y of s is 1 over s squared, but there's one last thing we have to do. We don't want to know what capital Y of s is. We need to solve this original function. These were functions of t, lowercase y of t, double prime of t, minus y of t equals negative t. I need an answer in terms of my original variable t, not in terms of the variable s. So I'll take the inverse Laplace transform of 1 over s squared to get my final answer. Let me make a little bit of room. I'll just come back up here to the top to finish this out. All right, so what we know right now is that the Laplace transform of y of t, remember y of t is what we're trying to find, the Laplace transform of what we're trying to find equals capital Y of s, which is 1 over s squared. So then, if I take the inverse Laplace transform, this means that the inverse Laplace transform of this function 1 over s squared is equal to y of t. Okay. Now, fortunately, we know what the inverse Laplace transform of 1 over s squared is. Look back at your table of Laplace transforms, and we see that the Laplace transform of t is 1 over s squared. So the inverse Laplace transform of 1 over s squared is t. So we get y of t equals t. And you can fairly easily verify that this function works in this initial value problem up here. If I plug 0 into this function, I get 0. If I take the derivative of this function, I get 1. So y prime of 0 will be 1. And if I do y double prime minus y, I will get negative t. So this function is the solution to our initial value problem. And we solved this using a new technique. Again, if you had tried solving it using method of undetermined coefficients or variation of parameters from chapter 4, you would have gotten the same answer. And it may seem a little bit silly to do all this Laplace transform stuff, when in this case we could have solved this pretty easily using those other techniques. But the point is to see kind of how the process works. Once you see how the process works, then clearly there's going to be some situations where the Laplace transform is going to be a much nicer approach than anything we've talked about in chapter 4. And there will also be some scenarios where the stuff we talked about in chapter 4 just won't work at all, and Laplace transform is really our only option. All right, so this is just kind of an introduction to this topic of solving differential equations with the Laplace transform. If you watch the next few videos, you'll see a few more examples of how we can use this.